What's going on, everybody? The study of trigonometry allows us to be introduced to a variety of new worlds, and one of those new worlds is the world of vectors. These are things that allow for us to describe in nature those things that really cannot be described just with a single number. These are things that don't just have magnitudes to them, they have magnitudes with a direction. These are things like wind, force, momentum. These are things that have a magnitude and a direction to them. And so they require actually more than one number for them to be fully described. And it's those packages of numbers for their full description that we call vectors here. So this is going to be a really important and seminal session for us here. So let's take some time before we go into it to empty our minds, open ourselves up so that we can be fully present in the moment here, to be fully alert, lose your mind, and come to a full sense of awareness. Take some time for that. I gotta say, I love this thing so much because you're getting exposed to something that's really important here. Vectors are used in physics, some in chemistry, it's used in engineering, electricity, magnetism, weather forecasting, statistics. There are so many places in which we're using these kinds of things that you're about to be introduced to today. This is a good day. So let's start here with defining what a vector is. A vector is, like I said, something that has a magnitude and a direction here. So its direction, you can see, is represented by the direction of this arrow. Its magnitude is represented by its length here. And in so doing, we can describe this as what's called a directed line segment here, one that starts at an initial point, which we'll call P, and ends at what we call a terminal point, labeled in this case Q. Like I said, this is a directed line segment, and one of the ways in which we label this is PQ, starting at the initial point, ending at the terminal point here. You can see it's the two letters with a little arrow going above it from left to right. Another way in which we label vectors is with, believe it or not, a capital, not necessarily capital, but a boldface letter that is non-italicized here. That's the way textbooks tend to do it. When it's something that you're writing in on your own sheet of paper, we generally can't write boldface very easily. So I'll see people do this. Write the letter V and put a little squiggly underneath it. That's oftentimes an alternate means of saying this thing that I'm describing here isn't just one number, it's multiple numbers put together in what's called a vector. We describe the magnitude of a vector, that's the length of this vector, with these symbols that are much like the absolute value signs, except that there are two of them instead of just one of them. So when we're describing this this expression here, what we're saying is the length of this vector here, or its magnitude. And here's a place where we run into vectors quite a bit here. Let me just give you an example here. This is from a website. Let's see if I can pull it up here. Yeah, right here. This is a website called vertusky.com here, and as you can see, it shows you actually multiple kinds of information here. Notice first the colors. The colors indicate temperature, and so you can see obviously in Florida these temperatures are in the reds and in the oranges here. These are warmer temperatures. Up in the upper Midwest, these are colder temperatures. In the blues and the blue-greens. Here is where we are in the Colorado Front Range here. It kind of looks like it's raining everywhere, but it's actually not rain. What this is showing is wind direction and wind speed here. So we can see here that primarily south of Greeley, Colorado, and really north of Colorado Springs, the winds are generally out of the west, moving at a pretty consistent rate here. You can see that south of this, right in here, perhaps this is a front line or something, we have winds that are actually coming out of the north. It looks like they converge somewhere in here. So we're seeing here actually two different kinds of things. Information that can be described just as a magnitude here, which is exemplified by temperature, and we have things that really require two pieces of information at least, a magnitude and a direction, to describe their full reality, so to speak. It's just one of many examples of how we use this. So let's talk about two vectors here. I'm showing two vectors directly above me here on this grid that are labeled with a U and a V. We've also labeled these as vectors PQ as well as RS here with the starting and ending points. And what we want to ask here is whether or not these two vectors are equivalent. And what does that mean? Two vectors are equivalent if they have the same magnitude and direction. They're in separate locations here, but do they have the same magnitude and direction? Well, here are the points that these two vectors start and end at. Here's P and Q, here's R and S. And so we can evaluate magnitude using the distance formula by measuring the distance from this first point to this second point. And this is what the distance formula looks like. It's the square root of the differences in the x values squared plus the differences in the y values squared. So if we add those squares together, then take the square root of that, then we get the distance from here to here. By the way, this is all based upon the quadratic formula. It's from the Pythagorean theorem here. Because if I draw this triangle here, if I'm wanting to know this distance from here to here, this distance squared should be equal to this distance squared plus this distance squared. Well, this distance squared here is the difference in the x values between P and Q. And this distance here is the difference in the y values between P and Q here. So if we take the difference in the x values, square it, take the difference in the y values, square it, add those two squares together, then take the square root of it, then we're going to get the length of this hypotenuse here. We're going to find the distance between these 2 points, or the magnitude of this vector here. We find that for vector PQ, its magnitude is the square root of 45. Let's see if we get the same thing for the other vector here. When we find the differences in the x values and the differences in the y values, we square each one of those, then add them together. Once again, we get the square root of 25. So they at least have the same magnitude. Let's also test if they have the same direction here. Okay, we evaluate direction by calculating slopes. So if you recall, when you were finding the slope of a line in algebra here, change in y over change in x, rise over run, all of that stuff, this is where we get to use that to see if these two vectors here have the same slope. In other words, do they have the same direction that they're pointing into? So let's first of all calculate the slope of this vector here. 3 minus 0, that's the change in y, all over the change in x. 1 minus negative 5, that's 1 plus 5, so that's positive 6. 3 divided by 6 is the same thing as 1/2. We can reduce that fraction to 1/2. Let's try the same thing with vector rs here. That's 3 minus 0 over 6 minus 0. That's 3/6, or again, 1/2. So they have the same direction. We already know they have the same magnitude. Vectors u and v are equivalent. Something else here, and I'm going to remove my face here so you can see this. We say that this vector v here is in what's called standard position, since its starting point here is at the center. It's at the origin, and so that defines this vector as being in standard position. All right, so try this problem on your own here. This is a problem in which you're basically doing the same thing as before. You're given two vectors here, vectors u and v, and you're told what the endpoints are of these two vectors, and prove that these two are equivalent. Remember, that involves finding that they have the same magnitude and the same direction. Take some time for that. Welcome back. Well, this is another instance in which you are calculating magnitude and direction of both vectors to see if these two things are in fact equivalent. PQ and RS both have the same magnitudes here at the square root of 10, and you found that the slopes are exactly the same, so these things not only have the same magnitude, they also have the same direction. Vectors U and V are equivalent. Okay, let's introduce here something called components of a vector here. And I think a good way for me to introduce that to you is through an illustration here. I'm just going to grab some kind of random object here, a quarter that's on my desk, and I have our trusty trigonometry textbook here. Now, if I press down on this quarter straight down into the book, then the vector of the force that I am applying to this quarter is perpendicular to the book. It extends directly downward. It has no force that's being extended in any direction here whatsoever. It's just something that's completely down. If I apply a force to this side of a quarter, in which I'm just edging it alongside the surface of the book here, I am applying a force that's in this direction. There's no downward component to it whatsoever. There's no component this direction or this direction or this direction. I'm already using the word. I probably shouldn't do that, but you get the idea here that I'm moving this in this direction. I'm applying a force in this direction, or I'm applying a force in this direction. What if I apply a force diagonally in this direction here? You might be able to say that there is a component of this force that's pushing the quarter in this direction, but there's also a component of this force that is pushing this quarter into the textbook here as well. There is a perpendicular component and a parallel component to this force that I'm applying diagonally here. This component idea is something that we will explore just a little bit more here. This is how we do this. The component form of a vector here can be described really as two components, just like I did with the quarter on the textbook here. V1 and V2. This thing is diagonal, so it kind of has components in two different dimensions here. And let's explore how we calculate that and how we can work with it. So a vector that is in standard position, this came out of the origin here, it can be uniquely represented by the coordinates of its terminal point, because you know this is 0, 0, so it's really just its terminal point here that defines the vector itself. So V1 and V2 are the coordinates of this point here. This is the component form of a vector written as this. So we can also describe this vector as being the x component and the y component. The portion described here by V1, that the vector is pointing in this horizontal direction, we have this component here described by the vertical coordinate V2 that describes how much this arrow is pointing in this vertical direction here. So coordinates to components here. So the coordinates V1 and V2 are the components of vector V. And if both the initial point and the terminal point lie at the origin, in other words, if this terminal point here is back here at the origin where the vector is supposed to also begin, then the vector is what we call the zero vector. It doesn't go anywhere. So the component form of vector V here, which you can see described with these two ending coordinates here, with initial point P, P1, P2, and terminal point Q, Q1, Q2, is given by this. So if we want to describe this in terms of component language here, and the way that we describe it that way is by using these sort of less than, greater than forms of the parentheses that we were using before here. So we have one component of the vector and we have another component of the vector here. So this is actually the x component of the vector and the y component of the vector here in this context. Once again, this is the x component and this is the y component here. So when it starts at the origin, then the difference in the x coordinates is just going to be the place where it ends, and so it's just going to be this coordinate here, and the differences in the y values are just going to be the ending component here. So it'll be this simple here. When the vector is not in standard position, when it starts at point P1 and P2 and ends at point Q1 and Q2, then we have to find the differences between those coordinates in order to find the components of the vector here. So Q1 minus P1, that's going to be our x component of the vector, and Q2 minus P2, that's going to be the y component of our vector. And the magnitude or length of the vector v is given by this. We've already seen this before. The way that you calculate the magnitude of this vector is through this distance formula here. But if this is coming out of the origin right here, which is 0, 0, then these things drop out, and we're really just representing it with two coordinates, the ending coordinates up here, v1 and v2. So it just becomes the square root of v1 squared plus v2 squared. So when you're describing this in terms of components, the formula for its magnitude sure becomes a lot easier. Here's some extra little things here. If the magnitude of vector v is equal to 1, then there's a special name for this vector here. It's a unit vector. So any vector that has a length of 1 is a unit vector. If the magnitude of v is 0, then v must be the 0 vector. And two vectors you can see described here as just a single letter or with their components. These two vectors are equal if and only if their first components are the same and their second components are the same. Well, that becomes a little easier than subtracting off the coordinates and seeing if they're the same, initial point to terminal point. We only have to compare two sets of numbers here in order to be able to determine if two vectors are the same if we're looking at components. So let's find the component form of a vector here. Find the component form and magnitude of the vector v that has the initial point here and the terminal point here. All right, so we have our 2 points that we're working with here. Here's point P, 4, -7. That's going to be just labeled as P1, P2. And Q will be similarly labeled as Q1, Q2. And so here's how we do this here. We want to first of all find the first component. That's going to be the x. That's going to be determined by the difference here in the x components of these two vectors here. So Q1 minus P1. It's the destination minus the starting point. Here's the destination minus the starting point. So Q1 minus P1. So that'll be -1 minus 4. -1 minus 4, that's -1 plus -4. The total here is -5. So -5 is our first component. We can find the second component in exactly the same way. We're now subtracting off the y component, the y coordinate rather, the second coordinate for each of these ordered pairs here. So Q2 minus P2, that's 5 minus -7. 5 minus -7, that's 5 plus +7. So 5 plus 7 is 12. So the second component of this is 12. So -5, 12 forms the components of vector v. And we can also describe what the magnitude is of v by using our usual distance formula here, simplified for the fact that we're working with components rather than coordinates starting and ending. So -5 squared is 25, 12 squared is 144. We add those together to get 169, which is a perfect square. The square root of 169 is 13. So that's the magnitude of vector v here. So try this one yourself here. It's a very similar problem. Find the component form and magnitude of the vector v that has the initial point of this and the terminal point of this. Take some time for that. Welcome back. Well, this might have provided you with some good additional practice exercise with the process of adding and subtracting positive and negative numbers here. What we've got here is -7 minus a -2. Subtracting a negative is the same thing as adding a positive. So this is the same thing as -7 plus +2. That would be -5 here. All right, so coming back to the fact that we took a look at that map, which showed temperatures being represented just as locations and magnitudes, and then we had the winds over top of it being described as vectors, we now live in a world where we've got two different things to know here. We've got vectors that can be described as a magnitude and direction. These require, at least in 2 dimensions, they require 2 numbers in order to fully describe. And then we have these things, which has been everything we've talked about up until now. These are scalars, quantities, things in nature that really only require one quantity, one number in order to represent them. All right, and so what is the new math that we have to have with scalars and vectors? Can a scalar and a vector add together? Can they subtract? Can they multiply? Can they divide? We know how to work with scalars, how to make those add and subtract, multiply and divide. Can vectors add and subtract and multiply and divide and all that sort of stuff? So let's talk about that for a little bit. First of all, vectors and scalars cannot add, but they can multiply here. So if I've got a vector here and I multiply it by 2, what that's going to do is it's actually going to double the length of this vector here. It's not going to change the direction whatsoever, but we're going to basically multiply both components here by 2. So it has the same direction, but it's got twice the magnitude. If we multiply v by 1/2, you can probably predict what's going to happen here. It's half as long. We've multiplied both components here by 0.5. Now what happens if I multiply this by -2? Here's the one caveat to saying we can't change its direction. We actually can if we multiply it by something negative. We're multiplying both components by a negative number. That reverses the direction of the vector here. So it was going in this direction, now it's going in this direction, and the fact that it was a -2 means that it has similarly doubled in length. And so the general rule here is that when we're adding these things, when we're multiplying these things together here, the product of a vector v and a scalar k is the vector that is the absolute value of k times as long as v. Now what is that saying here? That means that both this vector here is twice as long as this vector, and this vector also is twice as long as this vector. They both were doubled in length because it's, in terms of magnitude, it's not about whether or not this scalar that we're multiplying it by is positive or negative. We're really, the magnitude of this is really dependent upon the absolute value of this constant that you're multiplying it by. Absolute value of 2 is 2. Absolute value of -2, also 2. Both of these things are being doubled in length. That's what's being said here. And so the vector is now the absolute value of k times as long as it started. When k is positive, the vector retains the same direction. When k is negative, it switches direction. And so to say this in a kind of tight, packed and somewhat elegant way here, if we take any scalar k, multiply it by the vector v, basically what we're doing is we're just multiplying each component by that scalar k. Now how about if we want to add 2 vectors together here? So here's an example. If we're looking down on a scene here, we've got a large heavy box that's being moved by 2 people here. One person is exerting this force, another person is exerting this force here. You can see that they're close to the same direction, but they're not exactly, there's some, there's a little bit of difference here. And so how do we figure out what's the combined force that they are applying to this box here? And that will probably determine, by the way, what direction that box is going to move when it actually starts to move. Well, here's how you add these 2 vectors together to get the combined force. Take u, here's its starting point, here's its ending point, and where this one ends, the second one starts. Here's the starting point of v. The ending point of v is right here. Now we just draw a vector from the start of this to the end of this, and we get u plus v. This is how we add vectors together, and it actually doesn't matter which one goes first. If we have v going first this time, v can go first, that's fine. So start and end here. Now u is going to start here and end here. We end up in the same place. It doesn't matter which order you add them, you get to the same place here, u plus v. And another way in which we can show that is that the way that we take two vectors here, u and v, and we add them together is to add all of the x components together and then add all the y components together. That gives us a combined value for vectors, for the vector here, u plus v. So here's an example of where this really comes into play in real life here. I don't know if you've ever done any plane watching, but sometimes you'll see planes coming into land on this runway here, and I don't know if you can tell this, but this plane is landing in a way that's a little askew when compared with the runway here. It's not landing straight, and there's a good reason for that. The reason is that it's apparently landing into a crosswind, which is trying to push the plane, in this case, from left to right. So it's actually having to fly into that wind just a little bit in order to be able to counteract that effect and go straight. We can describe this in terms of vectors. In reality, the plane is having to fly with its engines gunning in this direction here because when it meets this wind, which is pointing in this direction, the combined effect of both its engines and the wind makes it go in this straight direction here, v plus w. All right, so let's talk about some additional operations that we can do on vectors here. Can we take the negative of a vector? Well, the answer is yes. That's just basically multiplying a vector by -1, and all that does is it reverses its direction. We can say that it also just changes the signs of each one of its components. That's another way of saying that it reverses its direction. So we can take the negative of a vector. And because we can take the negative of a vector, that means we can not only add vectors together, we can also subtract the vectors, because subtraction is simply adding the negative version of a vector. U minus v is equal to u plus -v. And so how do we do that? Well, it just involves subtracting corresponding components here. The x components subtract, the y components subtract, and we get our value for u minus v. And we can actually see that graphically here. I think I'm going to have to hide myself again in order to do that. But here's vector u from before. Let's say the second person walks to the other side of the, well, actually, let's say this. Let's say instead of pushing the box, the person starts pulling the box. Perhaps this person grabs onto some handles and starts pulling with the same force in the opposite direction. Now we have u in this direction, and we have minus v coming in the other direction. What's the combined force and the direction that the box is going to move? It's now going to be in this direction here, u minus v. All right, so let's do some practice with this here, where we are taking a vector here and multiplying it by the scalar 2 here. Well, this is pretty straightforward here. Vector v has components -2 and 5, and in order to multiply that by 2, we just multiply each component by 2, and we get -410. For this second one here, we're taking vector w and subtracting off vector v here. Vector w has these components, vector v has these components. When we do that, we subtract off 3 minus -2, that's 3 plus 2, which is 5. 4 minus 5, that's -1. So w minus v is a vector that has these components, 5 and -1. Lastly, what's the vector that we get from taking v and adding 2w to that? So here we're multiplying this vector by a scalar. You can see this vector here now being multiplied by a scalar, and this is just v here. So multiplying this by a scalar, we get 6, 8. Instead of 3, 4, this becomes 6, 8. And when we add this to vector v, we get this, vector 4, 13. These are the components of this vector. Okay, so try this yourself here. I've got two vectors defined here, u and v. They have the components shown here. So find what vectors are being represented by each of these combinations here. Take some time for that. Welcome back. Well, perhaps you remember some properties of the multiplication table that you might remember from a child. 3 times 5, same number as 5 times 3. That's true for every part of the multiplication table. 4 times 7 is the same number as 7 times 4. That also worked for addition, didn't it? 3 plus 5, same thing as 5 plus 3. This is something called the commutative property, and it works with addition and multiplication here. It's one of the properties that we work with when it comes to manipulating numbers in algebra. There's also something called the associative property, which basically means that if you're going to add up a bunch of numbers here, it's okay to just set some aside and add those up, and then maybe set some aside over here and add those up, and then add those two sums together. Then maybe you have 2 left over and add those. It doesn't matter the order in which you group these things and start to add them together. That's true for addition. Again, it's also true for multiplication. And there's some additional things that perhaps you noticed when you were memorizing the multiplication table. Anything times 0 is just 0. Anything times 1 was just itself. And there's a few others that came up here. You also, in algebra, learned about things called the distributive property, where you could distribute something to both terms inside of a parentheses when you had a binomial factor there. If you take a number and you add the negative of that number, 3 plus negative 3, that's always going to be 0, so they'll sort of cancel each other out, like 3 minus 3. That's another property of mathematics here, and we're about to see that these vectors have very similar properties as well here. So if I show you this here, here's some properties of vector addition and scalar multiplication here. Here's the first one, and we saw this graphically as we were adding together vectors u and v here. So we started off this way, and then we found out, oh, we could switch them and add them this way, and they ended up in the same place, starting and ending there. So it doesn't matter which order you add them when you're adding vectors. So vector addition is commutative. It's also associative. It doesn't matter how you group them together here. You're still going to get the same answer as you're adding them together. Anything plus 0, any vector plus the 0 vector is, well, the 0 vector is not going to do anything to it. It's still going to be that same vector. Any vector plus the negative of that vector is going to give you the 0 vector. So you can see how these things parallel very strongly some well-known properties of scalars. Here's something else here. If I take scalar if I start multiplying this scalar by this vector here, and then I multiply this vector here by this scalar here, that's the same thing as multiplying these two scalars together and then multiplying that product by the vector here. So it doesn't matter which order you multiply if all you're just doing is multiplying a couple of scalars with a vector. We also have a kind of distributive property when it comes to adding a couple of when it comes to scalar multiplication as well. We can distribute this u to both of these scalars here inside of a factor that's a binomial. So c plus d times u, if we distribute that, we get cu plus du. We also have the distributive property when it comes to vectors on the inside and the scalar on the outside. So c times u plus v is equal to cu plus cv. So we can distribute it that way. And any vector multiplied by 1 doesn't do anything to it. It's still the same vector. And any vector multiplied by 0 becomes the 0 vector. And also, we saw this one really before. If we are finding the magnitude of a vector that's been multiplied by a scalar, that's going to be the magnitude of the vector times the scalar here. And it's not going to matter if you're just taking a look at the length of the vector. Remember, if this is a -2, we're going to get the same length of this vector here as if this is a +2. So the magnitude of this new vector here is going to be the magnitude of v times the absolute value of c here. This has to be positive in order to describe the new length, the new magnitude of this vector. All right, so let's get into a new thing here. We've actually introduced this a little bit here. Given a non-zero vector v, sometimes it's useful to create a vector in the same direction but with a length of 1, and this is called a unit vector. So if I've got a vector of 6 going in this direction here, and I just want to extract one piece of it here that just has it's in the same direction, but it just has a length of 1, this is a unit vector. So we find this by dividing this vector here that has a magnitude of 6 and dividing the vector by its magnitude, which is 6. So then we get a vector with the same direction but with a magnitude of 1. So from a formula perspective, we're wanting to get this unit vector here, so we take any vector, divide it by its magnitude, or in terms of multiplication, we're taking that vector and multiplying it by 1 over its magnitude here. So we're taking this fraction of its this fraction of its magnitude here, or we're dividing it by its magnitude. So the scalar u is a scalar multiple of v. That makes sense. So the unit vector is a scalar multiple of it. The vector u has a magnitude of 1 and the same direction as v, and again the vector u is called the unit vector in the direction of v. All right, so let's do this here actually. Let's find a unit vector in the direction of v is equal to -2, 5. The components of that vector are -2 and 5. And sometimes it's a good idea to draw a picture here. So if this has an x component of -2, that means it's going to the left. And if it has a y component that's positive, that means it's going up a little bit. So this, you can think of it as just traveling 2 steps in that direction, maybe 5 steps up. So this is about what the vector looks like here. So it's pointing to the northwest. It's a little bit more north than it is west because 5 is larger than 2. All right, and so here's how we find the unit vector in this same direction here. We have to take this vector and divide it by its magnitude. Well, what's its magnitude here? -2 squared, that's 4. 5 squared is 25. 25 plus 4 is 29. Its magnitude is the square root of 29. So what we get here is -2 over the square root of 29. 5 over the square root of 29. You probably should rationalize the denominator here. I didn't do that, but I probably should have. So, but this is nonetheless the value for the 2 components of this now unit vector u, which is pointing in the same direction as v, but has a magnitude of 1. We can verify that u is a unit vector by calculating its magnitude. It should be 1. Let's make sure that it is here. So here are its components. Let's square those 2 components and then take the square root of that after we add them. The square of this is going to be 4 29ths. The square of this is going to be 25 29ths. We're getting warm. That's going to be 29 29ths here. That becomes the square root of 1, which is just 1. It does indeed have a magnitude of just 1. This is indeed a unit vector. All right, so try this one. Very similar problem here. Find a unit vector in the direction of v, where v has these 2 components here, 6, -1. Take some time for that. Welcome back. Well, once again, we're seeing an instance where we are taking a vector and reducing it to a magnitude of 1 by dividing it by its existing magnitude. So taking this vector here, dividing by its magnitude, gives us a vector here that has a magnitude of 1. And we can confirm that it has a magnitude of 1 by, well, finding its magnitude. And in doing so, we get 37/37, which is the square root of 1, which is 1. Okay, so here's another kind of problem here where we are doing something similar to before, but with an extra step here. Find the vector w with magnitude 5 and the same direction as this. Okay, so this vector here has a certain direction. It's got some magnitude here. It's probably not a magnitude of 1, so we're not sure what that magnitude is, but we want to make it so that it has a magnitude 5. Probably the easiest way to do this is to find the unit vector in this direction. That vector, at least we know, has a magnitude of 1, and then just multiply that vector by 5, by the scalar 5. So let's first of all turn this vector into a unit vector. So we'll find the unit vector in the same direction as v, and we'll do that by using the same procedure in the previous problem. 2, 5, we're dividing it by its magnitude here. Negative 2 squared is 4, 3 squared is 9, 9 plus 4 is 13. Its magnitude is the square root of 13, and so we're dividing both of these by the square root of 13. And what we've got here now is a vector pointing in the same direction as v, but with a magnitude of 1. This is a unit vector in the direction of v. So to get a vector w with magnitude 5 and in the same direction as v, let's just multiply this vector, this unit vector here now, by 5. And what we get is this vector, 10 over the square root of 13, 15 over the square root of 13. Yes, I probably should have rationalized the denominators here, so sorry about that. But nevertheless here, this is an accurate representation of the answer here. This is a vector with a magnitude 5 and in the same direction of v. Let's actually take a look at this new concept here called standard unit vectors. We've talked about unit vectors before here. They're vectors that have a magnitude of 1. Standard unit vectors have a magnitude of 1, but they're pointing in one of the seminal directions of 2 dimensions here. This is pointing in the x direction. This is pointing in the y direction, and that's indicated here by its components. This has an x component of 1 and a y component of 0. This is pointing specifically in the x direction here. This has a x component of 0 and a y component of 1. This vector is pointing specifically in the y direction here. And we traditionally label these vectors as I and j. Do not ask me why, but that's just the convention that I was introduced to when I was taking trigonometry as well, and it works fine. So the unit vectors 0, 1, and 1, 0 are called the standard unit vectors. And these vectors can be used to represent any vector in anywhere in this 2-dimensional plane. By the way, as an aside, we can also define 3-dimensional vectors that are actually coming out of the screen or going into the screen, so to speak. And those require not 2 numbers for their description, they require 3 numbers for their description. We can get into vectors that are in 4 dimensions, 5 dimensions, 12 dimensions, 18 dimensions. We can go as high as we want here. It's kind of cool that we can get into these kinds of things where you really can't even visualize the vector any longer. You're just working with it as it in its component form is just a set of components like this here. But just to keep that in mind here. And in those cases, we would have multiple standard unit vectors in all of those dimensions pointing and after 3 dimensions, we wouldn't know how to draw the later standard unit vectors. We would just know that this is a standard unit vector in the 4th dimension, and this one is a standard unit vector in the 5th dimension, and so on. But the point is that these vectors can be used to represent any vector. We're coming back to 2 dimensions here now. Any vector v with components v1 and v2. And here's how we can do that. Well, the components of vector v are v1 and v2, and we might say that that's equal to v1 times this and v2 times this. In other words, it's v1 of these x values here and v2 of these y values, isn't it? So if this component here is v1, it's v1 uh, uh, v1 of these steps in the x direction here, and v2 of these steps in the y direction here. And so that means it's v1 times I plus v2 times j. So we can express this vector in terms of I and j according to what its components are. It's v1 of the i's and v2 of the j's. And the scalars here and here are called the horizontal and vertical components of v. The horizontal and vertical components of v. So I can come back now to my analogy with the textbook and the quarter. There's a vertical component of the force pushing the quarter into the book. There's a horizontal component of the force pushing the quarter astride the book. And if I'm pointing at it diagonally and exerting a force that's diagonal, there's a little bit of both, isn't there? And you can describe this, when we describe any vector this way, we call this a linear combination of vectors I and j. So however many i's, however many j's added together, that's a linear combination of vectors I and j. So let's write this vector here as a linear combination of unit vectors. The vector u has an initial point here and a terminal point here. Write u as a linear combination of the standard unit vectors I and j. Okay, so let's first of all find out what the components of u are here. We've got starting points and ending points here, and so we're going to have to take the ending point here, subtract off the starting point, so -1 minus 2, and then for the y component we have 3 minus a -5 listed there. Okay, so -1 minus 2, that's -3. 3 minus a -5, that's +8. So the components of u are -3 and +8. Well, that means that we can describe this as -3 of the the standard unit vector i's and +8 of the standard unit vector j's. So here's a very similar problem to that. Write this vector, which has this initial point and this terminal point, in terms of a linear combination of standard unit vectors I and j. Take some time for that. Welcome back. Well, just like before, the process here involved, first of all, finding the components of vector u, and then just representing those in terms of a linear combination of standard unit vectors I and j. Okay, let's do something similar to what we were doing beforehand. Remember when we were using vectors u and v, and we were finding out how to calculate 2u minus 3v, some combination of those vectors here. This is the same thing, except what we're doing is we're representing vectors u and v as a linear combination of these standard unit vectors I and j here. Well, how do we do this? Well, 2u minus 3v, that's 2 times, this is u, see that? Minus 3 times v. You can see that that's that. All right, so then it's just algebra here. Remember, I can distribute this, this scalar here to both of these terms. So this becomes negative 6i plus 16j. And this becomes minus 3 times 2i. That's negative 6i. And this becomes positive 3j. Right here. And then we have some things that we can add together here. Minus 6i, that's minus 12i. 16j plus 3j, that's 19j. Well, that's pretty straightforward, isn't it? You're just adding really like terms here. You can think of it as like terms. We're using a vector scalar form of the distributive property here in order to do this very same thing as before. All right, so try this one again here. Find 5u minus 2v when u and v are represented as a linear combination of the standard unit vectors. Take some time for that. Welcome back. Well, you can see that this representation of vectors in the form of linear combinations of the standard unit vectors really provides us with a nice convenient means for creating some linear combinations of these vectors here. 5u minus 2v, we're basically just doing the distributive property here and combining all the i's and all the j's together into the form for our final vector. Very, very simple here. Now, something here you might be asking. What does this have to do with trigonometry? And the answer to that question comes when we place one of these vectors inside the unit circle from trigonometry. Let me show you what I mean here. If I show you this here, this is the unit circle from trigonometry, and here's a vector. It turns out this is a standard unit vector because it has a length of 1, and it's going to be, at some point on this unit circle here. We can describe it as having an angle theta from the origin. We're defining it in the same way that we have done with trigonometry so far. You can also see that we can describe it in terms of this triangle here, which we've done since day one here. Just think of this now as being a vector, and this vector has components x and y. That would be the length of this side x here and the length of this side y here, describing those components. And what is the length of this side here? This is cosine of theta. Remember, cosine deals on the unit circle, deals just with the length, the position in the x direction here. And what's the y here? This is sine of theta. So take a look at these two components. What are they? They're cosine theta and sine of theta. Now we have our connection to trigonometry here. So as we describe this unit vector here, x and y, on the trigonometric unit circle here, this is cosine theta, sine theta, or in terms of I and j, that's cosine theta I plus sine theta j. And so the angle theta is the direction angle of the vector u, and let's say that u is a unit vector, which it is, with direction angle theta. If we have any vector v with the same direction angle, it's pointed in the same direction here, then we can write this. V is equal to its magnitude times the unit vector, times this unit vector u here. Since the magnitude of this vector is 1, this gets the direction right, this gets the magnitude right. And if we multiply those things together, we can get v here. We can also express this in terms of a linear combination of I and j here. So it's cosine theta times the magnitude of v here. So once again, this cosine theta here and sine theta, they get the direction of the vector right, and well, this gets the magnitude of the vector right, doesn't it? So we now have a new way of describing any vector in terms of trigonometric functions based on the direction that the vector is pointing. Since v can also be represented as this, as a linear combination of I and j, then the angle theta can be determined using this. So we have cosine theta and sine of theta here. So we can, if we take sine theta divided by cosine theta, or more to the point, if we take this component here of v and divide it by this component of v, the magnitudes of v will cancel each other out. You just have sine theta over cosine theta, and that's going to just be whatever b is divided by a. So in terms of this particular representation here, this is just going to be b over a here. And so if we're given in other words, if we're given a vector like this, and it has some scalar here multiplied by a and some scalar b here multiplied by j, then we can find out the angle at which this vector is pointing by saying tangent of theta is equal to b divided by a. We just have to take those two numbers and divide one by the other. And we get the arctangent of b over a, and we can find out what angle theta is. Okay, so let's use that to define the direction angle of each of these two vectors here. Let's first of all take a look at this one. Tangent of theta is b divided by a, so that's this divided by this. 3 divided by 3, that's 1. And where that happens is when theta is equal to 45 degrees. This particular one here, it's 4 divided by 3. Oops, looks like I made a mistake here. That should be positive 4. So this should be, the problem here should be 3i minus 4j. Sorry about that. Tangent theta is equal to b over a, which is equal to negative 4 over positive 3. Now the arctangent of positive 4/3 is this. The fact that it's negative like this will probably put it in quadrant 4, and so that's 360 minus 5313, which is 306.87. All right, so in the same way, find the direction angles of each of these vectors. Take some time for that. Welcome back. Well, I'm just realizing now that there's something I probably should have reinforced with you more here. How do I know that V is in quadrant 2? Well, the answer is in the coefficients here. If I've got something that has an x component of -6 here, then it's pointing in this direction here in terms of x, and it's got a positive y component. It's pointing in this direction in terms of y. This is a vector that's in quadrant 2. In the same way here, this is pointing in the negative x direction, and it's pointing also in the negative y direction. This is in quadrant 3. So that's how I knew, by the way, on this previous problem here, that this problem, which has a positive x component and a negative y component here, that this vector here is in quadrant 4 because of the signs of each of the components here of I and j. So that's how that works there. All right, so now let's try our luck here with some applications. And the first one we're going to be working with here is going to be an application that involves a plane that is flying in a downward direction here, hopefully not too steep in a downward direction here, but it's represented by a vector here that has a speed of 150 miles per hour. The angle below the horizon here is 20 degrees. It's actually a pretty steep dive here. So find the component form of the vector that represents the velocity of an airplane descending at a speed of 150 miles per hour at an angle 20 degrees below the horizontal as shown in the figure. So how do we represent this vector in terms of components? All right, so since the velocity vector v has a magnitude of 150 and a direction angle of really 200 degrees here, so I'm measuring this from this portion here. This is how we're measuring angles, as you recall, from trigonometry. This is our equation here. We can represent this angle v here as its magnitude times cosine theta times I, and magnitude sine theta times j here. We know what theta is. We know what its magnitude is. We can represent this in terms of a linear combination of standard unit vectors I and j here. So 150 times cosine of 200, 150 times sine of 200. So this becomes negative 140.96 I minus 51.30 j. We can write it this way, or we can write it this way in terms of our component form with the special little brackets there on the end. And this is actually a way of saying that the plane is actually moving. It's not moving 150 miles per hour in the horizontal. It's only moving 141 miles per hour in the horizontal. And in the vertical direction, it's actually moving 50 miles an hour down towards the Earth here. So you can describe this in terms of two velocities here, one in the horizontal, the other one in the vertical here. So that's a special way and a special bonus you can get from this particular problem. All right, so a very similar problem here. Find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour, but at an angle 45 degrees below the horizontal. So take some time for that one. Welcome back. Well, I represented the downward angle here in terms of an angle of 225 degrees. That's actually one of two options that I could have chosen. The other one would have been an angle of 315 degrees, which would have been the other downward quadrant here, choosing it to go in this direction versus this direction. But we get the same answer either way here. So we're going 70 miles an hour in the horizontal, and believe it or not, 70 miles an hour in the vertical as well. That's quite a descent for this airplane here. All right, we're going to switch here from planes to boats here, and we're going to return to my analogy here with the book and the coin here. Now, if you take a look at this coin that's sitting on top of this book, the force of gravity that is being exerted on this coin here is going directly downward. And if I turn the book just like this, you can see that, well, if I have to watch it so it doesn't fall off here, but I'm just going to turn it enough so that the component in this direction isn't strong enough to overcome the force of friction here. But the reason why there's a component in this direction is because now the force of gravity is diagonal just a little bit. It still has a component that's butting up against the book, but it also has a component that's trying to move the coin in this direction a little bit. And if it were not for the friction here, it would be sliding this coin off the book here. So how does gravity work with an object on a slanted surface here? It's always pointing downward here, but that means it might have a component going in this direction here if the surface that it's on is slanted. In the same way here, I'm showing you a boat that is on this slanted ramp here. This vector right here is the force of gravity, but as you can see, it has a component in this direction here where it's exerting a force on the ramp, and it also has a component in this direction right in here, which is trying to push the boat back into the water. Okay, and so the geometry of this is a little interesting here. So if I've got the boat here, there's my boat sitting on this ramp here, it's got a force of gravity that's always pushing it straight down here. But this force of gravity has a component that is hitting the ramp directly, but it's also got a component that's trying to push the boat back into the water, so to speak. All right, and as it turns out, how do we figure out what these things are? What angles are being described here? Well, as it turns out, we can just because we know the geometry here of this thing here, this is a ramp that's going up 15 degrees, and these two triangles here are actually similar triangles. So this one is also 15 degrees here. So we can use 15 degrees and some trigonometry to figure out the strengths of each one of these vector components here. That's what this problem is all about here. So a force of 600 pounds is required to pull a boat and trailer up a ramp inclined at 15 degrees up from the horizontal. Now think of what that 600 pounds is. It's not the force of gravity. That force of 600 pounds is what's needed to keep it from going into the water here. This is the force needed to overcome this force right in here. So that's just that component of this vector. So we've got to use that to find out what this larger vector is. It's going to definitely be larger than 600 pounds. I should have underlined that instead of horizontal. It's going to be larger than 600 pounds. But just how much larger, we've got to find out using trigonometry here. So the ramp is inclined at 15 degrees from the horizontal. How do we do this here? Well, the magnitude of angle, let me label my points here just like they are in the diagram. This is B, this is A, this is C. So BA is the combined weight of the boat and trailer. It's the force of gravity. BC is the force against the ramp right on here. And lastly, CA, which can be represented here or here, is the force required to move the boat up the ramp. That's the force needed to pull it up. That's 600 pounds there. Now let me go ahead and erase this. So you can see the rest of the calculation here. Hopefully this diagram is enough over here. All right, so since these two triangles are similar, then angle ABC here, this tiny little angle, is 15 degrees. And so sine of 15 degrees here is equal to opposite over hypotenuse. Opposite here being AC, that's the 600 pounds, and this hypotenuse here being the force of gravity, which is what we're trying to find. So we can solve for the force of gravity, which is BA, 600 divided by the sine of 15 degrees, which is 2,300 pounds. So the combined weight of the boat and the trailer is approximately 2,400 pounds there. All right, so do the same thing here. It's going to be slightly different than this diagram here, but I included this just in the case that it would help. A force of 500 pounds is required to pull a boat and trailer up a ramp inclined at 12 degrees from the horizontal. Find the combined weight of the boat and trailer. Take some time for that. So much of this process is just in the seeing, learning how to see all of these vectors and the way in which they interact with each other and the ways in which we can use them to solve problems here. Hopefully you were able to see this force of gravity here being represented by vector BA, the force against the ramp, being represented as BC, and the force trying to pull the boat down the ramp as being CA, even though the numbers here are different now. The angle of inclination is now 12 degrees, and the weight that's necessary, the force necessary to pull it up, is now 500 pounds. The equations are the same, and the weight here is 2,400 pounds. So the previous problem should have said 2,300, so now 2,400 pounds is correct. All right, let's switch back from boats back to airplanes here. We have an airplane that's traveling at a speed of 500 miles per hour with a bearing of 330. Now with a bearing, that means that we start at north and we move counterclockwise around in this direction, and so this angle here is 330, and so that means it's got an angle of 30 degrees from here to here. This is of course 90, so in our language we would say that this is an angle of 120 degrees, but nevertheless here this is 500 miles per hour going in this direction here with this angle, and it has a wind velocity that is pushing it off course just a little bit, perhaps, going in this direction here, and the wind velocity is 70 miles per hour in the direction north, 45 degrees east, so it's diagonal in this direction here, as shown in the bottom figure. So what's the resultant speed and direction of the airplane here? Okay, well, this is something where it's a good idea for us to figure out what all these components are going to be. So for V1, this is 500 times an x component here that is cosine of 120 degrees, a y component that's sine of 120 degrees. This is getting the direction right since we've got the magnitude correctly here. So 500 times this is going to be negative 250 in the x direction. That makes sense since it's moving to the left. And we have sine of 120 degrees times 500. That's 250 times the square root of 3. That's positive, which makes sense since it's going north. So that's the way we represent in component form vector V1 here. We can do the same thing with the wind vector here, 70 miles per hour, cosine of 45 degrees, sine of 45 degrees. That's 35 radical 2, 35 radical 2. And let's just add those things together here now. So this becomes negative 250 plus 35 radical 2, positive 250 radical 3 plus 35 radical 2. And if we add all those things together here, we get negative 200.5, 482.5. So that is our new vector that is going in this direction here. It's still negative in the x direction, still positive in the y direction. We can calculate what its magnitude is here now in the same way as before. 200.5 squared, 482.5 squared, add them together, take the square root. We get 522.5 miles per hour. So that's interesting because the engines are only pushing the airplane at 500 miles per hour. So apparently this wind is providing enough of a push that it's actually increasing the speed of the aircraft relative to the ground of another 22.5 miles per hour. And what's its new bearing? Well, the tangent of theta, and theta now is the way that we describe theta, which is up from this rightmost horizontal over here. That's this value divided by this value here, the y component divided by the x component. Remember, this is b over a, and we have this, and we just take the arctangent of that. And we know that it's in quadrant 2, so this is going to be 112.6 degrees here. If it's 112.6 degrees here, then let's see if we can reconstruct what that means in terms of its bearing here. 112.6, that means that this component right in here is 90 less than that, so that's going to be 22.6 degrees, which means that the rest of it's going to be 360 minus 22 0.6 degrees, so that's 337.4 degrees. That's its new bearing relative to the ground. It's true direction. All right, so take some time on this one here. It's a very similar problem. Repeat the same problem with an airplane traveling at a speed of 450 miles per hour with a bearing of 300 degrees that encounters a wind with a velocity of 40 miles per hour in the direction north 30 degrees east. So this is really giving you an exercise on being able to convert between bearing and north, the other ways in which we've described angles versus the way that we describe angles in our trigonometry class here. So take some time for this. Welcome back. Well, just like before, this involved taking two vectors, breaking them down into their constituent components, combining those components, and then recreating the vector back from scratch once again here. So we took the velocity vector of the plane as well as the velocity vector of the wind, broke it down into its constituent components, and we added those together to find the components of a new vector here, which has a magnitude of 451 miles per hour. So the engines are driving the plane at 450 miles per hour. We're just getting about a 2 mile per hour boost here from the wind relative to the ground. And we started off going at a bearing of 300 degrees. The wind is making it so that it's a bearing of about 305 degrees from the northern from the North Pole heading here. Just think of all we've covered today. There's so much stuff here. I know this video is long, but it's really a lot of good stuff. If we take a look here at what we've done, do you know how to, first of all, represent a vector as a directed line segment? So can you picture vectors in your minds here? Can you also write a vector in component form? You know, one component in this direction, another component in that direction. Can you perform vector addition and scalar multiplication? Do you remember how to add those vectors together by placing them end to end and then drawing the resultant vector from the start of the first one to the end of the second one? Do you remember how to double a vector, triple a vector, multiply a vector by a negative number, all that stuff with scalar multiplication? Can you write a vector as a linear combination of I and j? You know, those unit vectors there. Can you combine? Can you write it as a linear combination of those? Can you find the direction angle of a vector? This is where a lot of the trigonometry comes into place here, where that x component is cosine theta and the y component is sine of theta. So this is a lot of stuff here. And also, can you solve some real-world problems using some of these vectors like we did here? I just have to say, this is such good stuff here. There's so much here that really you have no idea just how many worlds this is opening up to you. I've said before that the answer that I oftentimes give to the quintessential math student question, when are we going to use this, is you tell me. Just go outside and see all of the ways in which things have magnitudes and directions, forces, momentum, energy, acceleration, gravity, winds, electricity, magnetism, all of these things out there that either involve a force being applied to something or things moving can be described using this new language, this new terminology of mathematics that you've now learned today. This is a good day, and I'll see you in class.